Greeting. Peace be with you. In this video, I will demonstrate how Raspberry Pi Pico can be used to drive a simple speaker playing song melody by simulating sound wave on the speaker's terminals. To make things more interesting, the initial basic experiment will be enhanced to use DumbDisplay as UI, providing a few playback control buttons, and a simple keyboard for playing notes. To connect to DumbDisplay Android app, Bluetooth connectivity is used. The connections are very simple. For connections of the speaker, connect the red wire, the positive terminal of the speaker, to GP5 of Pico. Connect the black wire, the negative terminal of the speaker, to a ground pin of Pico. For the optional Bluetooth connectivity using HC06, connect BCC to BBus of Pico. Connect GND to a ground pin of Pico. Connect RXD to GP7 of Pico. Connect TXD to GP8 of Pico. That's it for the connection wirings. Now, let's review the sketch that drives the speaker playing a song by simulating sound wave. Line 1 defines the pin connected to the speaker positive terminal. Line 4 starts defining the routine, to note index. Be advised that note index can assume values from 0 to 11, referring to the 12 notes in an octave. The two parameters to pass to the routine are name of the note and half note indicator. Note names are C, D, E, F, G, A, and B. Half note indicators are sharp or flat. In the routine, lines 8 to 16 convert the note name to note index. Lines 17 to 21 adjust the note index based on the value of half note. Line 22 returns the note index worked out. Line 28 starts defining the routine get note frequency. The two parameters passed to it are octave and note index. Note that octave can assume negative value, and note index is the value returned by the routine to note index. Line 31 returns the value rounded to the nearest integer. Line 35 starts defining the routine play tone. It is the code that actually drives the speaker playing tone by simulating sound wave. Two input parameters are frequency and duration in milliseconds. Line 36 declares till micros to indicate when the tone should end. It is the current millis plus the note duration. Note that till micros is in microseconds. Line 37 declares wait micros to indicate how long each provoke of the speaker should delay for. Basically, it is the half of the sound wave wavelength. Line 38 declares local variable high to indicate how to provoke the speaker. By setting the speaker's positive terminal to high then low, it sort of simulates square wave on the speaker. Line 39 starts the loop. In the loop, line 40 finds out how long the loop should go on. Lines 41 to 43 check that if the loop should end, if so, break out of the loop. Otherwise, line 44 signals high or low to the speaker positive terminal. Line 45 toggle the local variable high. Effectively, if this time is high, then next time will be low. Line 46 delays the amount that is required to simulate the correct frequency of the square wave. Line 52 to 54 declare the song melody notes and its tempo, with three constants, song, octave, and beat. For each song note, the constant song stores note name and half note with 2 characters. The constant octave store the octave of the note. The constant beat store the beat of the note. Line 56 declares the constant beat speed to control the tempo of the song. Line 59 to 61 define the setup block, which simply sets the pin mode of the pin connected to the speaker's positive terminal. In the loop block, line 64 starts looping the song notes. Line 66 and 67 get the note name and the half note of the song note to play. Lines 69 to 72 check if the note name is the value 0, that is the end of the song is reached. If so, break out of the for loop to play the song again. Line 75 gets the note index from the note name and half note of the note to play. Line 76 gets the frequency of the note. Line 79 calculate the duration to play the note for, in milliseconds. At last, line 82 play the note. This concludes the sketch. Let's hear the demo. Wow, it is fundamental. Now, I will try to add UI to the sketch to make it more fun. I will use DumbDisplay as a remote UI to control the music playback, as well as simulate a simple piano keyboard for playing some key notes. Let's review the sketch. Line 3 defines the pin connected to the speaker positive terminal. Since DumbDisplay supports playing tone via your Android phone, a physical speaker is optional. In case a speaker is not connected, you can comment out the speaker pin defined by line 3. Line 9 defines the macro Bluetooth. It is here to indicate that Bluetooth should be used to connect to DumbDisplay Android app. If Bluetooth module is not connected, comment out line 9. In such a case, you will need DumbDisplay Wi-Fi bridge to make the connection. If the macro Bluetooth if defined, lines 14 to 18 declare DumbDisplay object using Bluetooth connectivity. Notice that the baud rate configured as 115,200. Otherwise, lines 22 and 23 declare DumbDisplay the basic way, in that it will try to make connection via USB serial connectivity. Line 28 starts declaring the routines as previous sketch. Lines 76 to 80 declare the global variables as previous sketch. Lines 85 to 88 declare some constants that configure the dimensions of the UI on DumbDisplay. Lines 92 to 101 declares an variant of the routine play tone, which is used by DumbDisplay UI code to play tone. The added parameter, play to speaker, tells if it is desired to play tone to the speaker attached, or to the connected DumbDisplay in your phone. If play to speaker, then it will play the tone the same way as demonstrated in previous sketch. Otherwise, it plays the tone via DumbDisplay app. Since playing tone to DumbDisplay app takes no time, an explicit delay is needed right after playing tone to DumbDisplay. Line 104 declares the global variable play to speaker. Apparently, this global variable is to control whether tones should be played to speaker for to connected DumbDisplay on your phone. Lines 106 and 107 declare the global variables play and restart. Play controls whether the song should be played or not. Notice that the global variable play is initialized to false. It means that song will not be automatically played. Restart signals that play song should start from the beginning. Line 109 declares the global variable ad hoc frequency. This variable will store the tone frequency to play when key on the DumbDisplay is pressed. Lines 113 to 115 declare 3 LCD DumbDisplay layers to simulate 3 buttons to vary those 3 variables. These 3 LCD layers will be created and set up in the setup block, play layer for the variable play, restart layer for the variable restart, and target layer for the variable play to speaker. Line 118 starts to declare the DumbDisplay feedback handler. If the layer pressed is the play layer, that is the play button is pressed, lines 120 to 125 toggles the global variable play, to indicate that song should be or be not playing, as well as set the play layer background to indicate on/off. If the layer pressed is the target layer, lines 127 to 132 toggles the global variable play to speaker, to indicate that song should be or not be played to the attached speaker, as well as set the target layer background to indicate on/off. If the layer pressed is the restart layer, line 134 sets the global variable restart to true, so that song player will restart from beginning. If it is key press, line 136 get the note info data from the layer's custom data string. Then line 137 and 138 turn the note info into the keys octave and note index. Followed, line 139 and 140 assigned to the global variable ad hoc frequency, the keys frequency converted from the octave and note index extracted from the keys note info. Note that when the global variable ad hoc frequency is set, the note will be played in the loop block. Lines 144 to 146 declare the DumbDisplay idle callback, which will be called when DumbDisplay library detects idle, that is disconnected. Notice that the idle callback simply set the global variable play to false to stop playing the song. Line 149 starts declaring the routine setup key, which is used to create a piano key on DumbDisplay, represented by a graphical DumbDisplay layer. Notice that two parameters are required. Octave offset is either -1, 0 or 1, which is basically octave I have been talking about all along. Note index, well, it is note index. Notice how line 170 to 173 store the octave and note index to the custom data of the layer as note info mentioned previously. Line 195 to 202 declare the routine setup button for creating and setting up the three buttons mentioned previously. In the setup block, line 211 calls DumbDisplay object method record layer setup commands. By recording layer setup commands, reconnection to DumbDisplay app is possible. Line 213 sets up a pin frame for pinning the different layers on the DumbDisplay. Basically, it is just like a canvas where the layers are drawn. Lines 215 to 219 call the routine setup key to create, configure and pin the key layers on the pin frame. Lines 221 to 223 call the routine setup button to create and configure the three button layers. Line 225 to 229 pin the three button layers on the pin frame. Note that the three buttons are auto-laid out horizontally. Line 231 instructs to play back the recorded layer setup commands. As the last setup, line 233 sets the idle callback declared previously. In the loop block, line 237 starts looping the song's notes. Notice that the for loop is basically just a loop. Line 239 calls DD yield to give a chance DumbDisplay library to do its work. Line 241 to 245 check if ad hoc frequency is set to some frequency, that is when a key on the DumbDisplay is pressed, play the key's frequency with a delay of 200 milliseconds. Line 248 to 252 check if restart is signaled by the global variable restart. If so, simply break out of the loop. Line 255 to 258 check if play is signaled by the global variable play. If not, simply continue the loop without executing the rest of the loop. As previous sketch, the rest of the loop will play the song's notes. Finally, line 278 and 279 increment the loop counter I by 2, 1 for the note, 1 for half tone. Now, let's see the demo.